Okay, so what we are trying to do again, looking at this particular slide, is to find this point, right? So find the point where you've got the minimum error rate on the test data. Okay, that's what we are trying to do here. So let's take a look at a tentative approach just based on common sense, how we might achieve this. Okay, now what R does is it adopts a process called cross-validation. But before we get into cross-validation, let's take a common sense look at how we might do this with this. Okay, so first we might partition the data into training and test, as we have always done. So let's say we then go ahead and build the full tree on the training data. Okay, so let's say this is the tree that we get on the training data. Pretty large tree with probably some small splits like you see here, 1%, 2%, 2%, 2%. These are all nodes with very few cases. So assuming that this tree was built on about 200 and 300 odd cases, right? So these are all things with 9 nodes, 9 cases, 10, 4 cases, 5 cases. These are small things. So clearly there is need to prune this tree. Okay, so how might we do that? We are looking, remember, for the part for the tree size that generates the minimum error rate on the test data, right? So while constructing the tree, after all, what is happening? We go through this process of creating splits, right? We keep on splitting. We start with all the cases as one node, which is our root node. Then we consider the first split. Now what we could do is, at the time before we have done any splitting, we have our tree with one node. The tree is simply the root node alone. Okay, how is it going to classify the cases? Simply by majority. In fact, the naive model. Okay, so we've got that tree before we did any splits. Okay, and that is our best tree of size 1. Okay, so what we could do is use that tree and run the test data through that tree. Okay, and find the error rate on a tree of size 1 on the test data. Okay, then we do our first split, and after doing the first split, we have the tree as it stands at that point. Okay, that is our tree of size 2. We could again run the test data through that and find the error rate on the test data for a tree of size 2, and so on and so on and so on, right? So for trees of various sizes, in fact, the tree that I showed you on the previous page has a size of 10, right? 3 plus 3, 6 plus 4, 10. That's the maximum size that was there, right? So in this process, while we are going through this process of generating this tree, we'll have initially a tree with one node, right? Then we'll have a tree with 2 leaf nodes. This is one leaf node initially, when that's the only node in the whole tree. Then we'll have a tree with these 2 leaf nodes. Okay, then maybe we'll have a tree with, once this is split, with this leaf node, that leaf node, that leaf node, right? So what we are doing is, as we create more and more rules, as we split, we are creating trees of different sizes, and all we have to do is to take the tree at each level and find out what its error rate is on the test data, right? Because after all, the test data is available, right? So we can go ahead and do this, right? So for many different values of n, up to 10, because 10 is the maximum number of leaf nodes we have in our present tree, we can find the error rate, right? So as a result of that, what you might get is something like this, right? So you've got the tree size, because as we built the tree, we got trees of different sizes. And for every tree size, we can find the error rate on the training data, because after all, the training data is available. We can also find for each of those trees the error rate on the test data. Okay, so you might end up with something like this. And after that, you can plot this, right? You can use Excel or you can use R, and you can actually plot this. So you see that the error rate on the training data is going down, and the error rate on the test data went down up to a point and then started increasing. Okay, so that's what, of course, these are numbers I just made up to illustrate the idea. These are not based on any reality. Okay, but I'm just giving you this as a potential approach to doing this. Okay, so when you do this, then you realize, okay, the minimum point where the test data has the minimum error is here, and therefore a tree of size 6 is good. Okay, so That way we have determined which is the optimal point in terms of the tree's performance on test data, right? So beyond this, clearly the error rate on the test data is starting to increase because we have started overfitting at this point. Okay, that's really what we are doing here. So this is a tentative approach, but there's a big problem with this approach. Okay, the big problem with this approach is that in order to find out what is the best tree size, namely 6, we had to use our test data to do that. Okay, see, after all, to say that the correct size of the tree is 6, that is still model building, and we ended up using our test data in model building. Okay, which is a big boo-boo. That's something we should not be doing at all. Test data should be independent and it should be reserved only for testing the model. It should not play any role in the model building process. It should be used only for testing. Whereas with this approach that we did, we've ended up using this test data for model building, and that's a big problem, right? So our independence of the test data got compromised. So what we would need is yet another set of independent data on which to test the model. Okay, but we've got a good idea of what's going on here. That is the reason I presented this as a tentative approach, just to explain to you what is going on.